And one thing I didn't get to last time that I want to just touch on very briefly is the solar wind. And hopefully we can get into it a bit more in detail when we talk about the sun, which is going to be a fantastic lecture because the sun is such a complicated and vital piece of this equation. And there's so many mysteries left about the sun too, which is really cool. The solar wind. Okay, so what is that? The solar wind is very interesting. And it plays into our life on Earth here too, and into our weather. And obviously, the magnetic field is, in some sense, repelling the. Yeah.
The solar wind, basically solar flares, and how that the atmosphere creates light.
Yeah. Let's talk about that. 1 second. All right. Real quick though, what we're going to do today is after I get through this, we're going to talk about the atmosphere, which does involve the outer atmosphere, which is this wildly electrified ball of ionized plasma, which is really important because it essentially acts very metallic-like, and we can do lots of cool things with it. And it also shields us from these terrible things coming from the sun, which would do us in very quickly. We're also going to talk about the origins of life, which several of you mentioned in your intro videos that you were interested in discussing. That's a hard one to talk about, so we'll investigate all the possibilities, but there's no clear-cut answers there, unfortunately. And then I want to talk about the extinction of life, too, which is kind of the back half of that story. So back to the solar wind. The sun, and I don't want to get too much into the sun today. I just want to mention this. There's a phase transition that happens at the surface of the sun, which is really fascinating and still being worked out. Now, scientists use this word plasma to describe matter that is in an unconventional state that we're not totally sure how to deal with. The sun, and there's something like 11 different types of plasma, and they vary in behavior from gases to liquids. At the surface of the sun, there is a great deal of, obviously the sun's very hot, and these molecules, they essentially are doing something which you can think of as like a sublimation, where the molecules are getting kicked off of the surface of the sun. They don't have the gravity at that distance to hold on anymore, and they fly off into space. And what's really fascinating is they actually accelerate. They get faster as they leave the sun, which is very bizarre. And this is because the gravity is actually falling off, like we talked about, with an inverse square relationship. So these tiny little atoms and molecules are being ripped off and ejected, and they speed up, and they're going at quite a click by the time that they reach us. And this idea of solar wind was thought of rather recently by this really put together by this guy named Eugene Parker, who is his namesake is borne by the Parker Solar Probe. I think he's the only living person to have a space craft named after him, which is really interesting. Parker and some of his colleagues put together the fact that comet tails seem to always be pointed with respect to the sun. They're being the tail is always pushing away from the sun, which is bizarre because it was always thought that comets were flying through space and their tail would be out behind them. This didn't seem to be the case, and they realized that there was some he actually gave it the name solar wind. It seemed that there was actually a constant stream of material coming in towards us, and this checked out, and we're actually able to measure these things in orbit, the flux of these particles at this point. What else do I want to say about that? All right, we'll get more into exactly what's up with that plasmatic state of those atoms, because it plays into how we use radios on Earth. It plays into weather. It plays into so many different aspects that we'll get into in a minute. One thing that's really interesting is that the pressure, the air pressure in the atmosphere, essentially falls off with height. And we'll talk about what air pressure does, what decreased pressure does to atoms here in a little bit too, which is really important in terms of understanding why there's such an electrically conductive surface out there at the edge of the atmosphere that's capable of deflecting incoming objects, reflecting radio waves. This is pretty cool. So what this means is that down on the surface of the Earth, over here, you have about 1 bar of pressure. And what this means is that there's something like a kilogram squeezing every single centimeter of the Earth. And this seems really strange because you don't feel a kilogram on your head right now, which is very bizarre. And at the bottom of the ocean, for instance, there's something like 300 bars of pressure. And there's fish that swim around down there, which is really strange. And so you try to understand how you can have so much pressure upon you without being squished. And it comes down to this concept of equalization. If you've ever gone diving before, you have to sort of pop your ears as you swim down deeper and deeper. And this is because we all essentially have the same amount of pressure inside of us and on all sides of our body as what's coming down from the top. And so there's equal pressure pushing back as from the top, and we feel basically nothing as a result, which is pretty shocking. And this plays into some of the thick atmosphere theories that are on the fringe that we were playing with last time, because how can the large animals, the dinosaurs, take so much pressure? Well, they had the same amount of pressure internally as well, so it wasn't a problem. Okay, so the atmosphere basic layout is kind of fascinating. If you look way down at the bottom, you have the troposphere. And this is the atmosphere that we're used to. This is essentially where all of the clouds are. This is where all of our weather is. And slightly above that, you have this nice ozone barrier, which we'll talk about in a second. And the stratosphere begins, which is very thin and very cold. I'm going to show you a really cool interactive globe that you can play with on your own too, to check these out. So the circulation of these different currents down in the troposphere generates the wind, generates the condensation required, for clouds, which really has to do with the interfacing of cold and hot air mixing and precipitating out different ice crystals and different molecular water. This doesn't seem to be at play so much up in the stratosphere. It's just too cold for any convection that's appreciable. So let's talk about ozone a little bit. So ozone is a strange form of oxygen, and the history of oxygen on our planet is really important. We'll get to that when we talk about life. But ozone is essentially a triumvirate of oxygens. There's 3 of them. And ozone is, there's something about its particular geometry which allows it to absorb ultraviolet radiation, which is very useful because otherwise it would be streaming in and causing all sorts of damage. Ultraviolet seems to be particularly resonant with our DNA. You can think of your DNA as having a sort of wave-like structure to it, right? It has these coil helices to it. There's something about the periodicity of the DNA coil which seems to resonate very nicely and catastrophically with ultraviolet radiation. Resonance is a really important concept, right? Do any of you know about the Tacoma Narrows Bridge up there? Yeah, it's kind of, can you tell us about it at all?
The ones that hit it, but then it started to vibrate so much that it basically fed into itself.
Right,
It
right.
just kept rocking and rocking and harder and harder and harder.
Yeah. So the winds, it wasn't just that there was strong winds, it was that the winds were occurring at a pulse which was commensurate with the wavelength of the bridge itself. And so you get a bending of the bridge exactly as you get a gust, and this sends it into this wild resonance, which is catastrophic. I would hypothesize there's something similar going on with UV radiation and DNA. There's something about that impulse which is commensurate with the actual wave structure of the molecule, and it's bad news. So this is actually the ozone layer. If you were alive in the 80s, this would have been the talk of the town, much the same as climate change is today. I barely remember this from my childhood, but it's actually one of the real success stories of modern science, which I think that it's worth remembering. In a world where people are often very skeptical of science, sometimes science gets it wrong. But in this case, people really came together and made a crazy change that really saved this. So folks were studying ozone, and they realized that these particular molecules that were being used as coolants and also in different aerosols were particularly destabilizing to ozone, to the extent that there was a hole appearing in the ozone in the north. And they actually got together, and this is a time lapse from 73 all the way through 2016. They made a change in the mid-80s. I wish it would stick around on the last slide a little bit, but you can see this gap closes towards the 2000s. What happened was the scientists got together with the politicians, and they enforced an international, they recommended and pulled off a global enforcement on the production of these particular coolants. And they eradicated them. They actually stopped them from happening, from being built, from being manufactured. And they rather remarkably fixed a hole in the atmosphere this way. And I don't think there's any precedent in history for something so large scale and global being accomplished. This was in the era before the internet and everything, and people still made it happen. And what's very strange is today we have a very linked up global society, but it's also very fragmented. There's not so much cohesion amongst the way that people do science in different countries. People aren't necessarily working together as well as we'd like them to. And it's actually remarkably difficult to get people to sit down in a room together and talk about what we should and shouldn't do as a global society right now, which is very strange because they were able to pull it off in the 80s. Another thing they did in the 80s, which was really cool, is they discovered cloning technology. You guys have maybe heard a little bit about this, about cloning. This is obviously not a biology class, but we've, of course, have the ability to essentially make duplicate organisms at this point. Well, as soon as they invented this technology, all of the scientists in the world got together and had a symposium, and they said, let's stop cloning until we figure out how to ethically do this properly. And they pulled it off, too. They really did come up with some guidelines, and that's why you can't just go down to a shop and make a clone of yourself. It's not that we don't possess the technology to do it. It's that we decided that's probably a bad idea. Yeah. Yeah, it is. It is. And so this was another success story of scientists being able to regulate activity. It's not so clear that we're able to pull that off right now. So we have developed all sorts of really interesting technologies lately. One of them, we have the ability to edit genes now. There's a technology called CRISPR-Cas. There hasn't been the same level of international collaboration on how to regulate that technology. Nobel Prizes were given. It's a very brilliant invention, but it's not clear that it's agreed upon how that will be used in the future, because there's all sorts of strange ethical issues that crop up. Do you really want the ability to eradicate different genes that right now are contributing potentially to deleterious effects, but also potentially to great stability? It's very difficult to pick apart complexity. If you take one gene out of a body, what are the other avalanche effects that you're going to destabilize in the long run? And so this hasn't been worked out yet. And I think that this is sort of reflects the lack of global cooperation that's going on amongst scientists right now. And I hope that we can figure that out. Because we did it once already, and hopefully we can hang together. There's a great deal of anti-globalist sentiment right now, which is like totally well-founded in some real suspicions, but it's also worth noting that if we're ever gonna make it off of this planet and find some other places to live, down the line, we're gonna have to work together. And so we're gonna need some sort of a way of getting together as a whole planet and making decisions. And it's not clear that we can do that right now. We have the UN, but it's very defanged. It doesn't have a lot of muscle. It can't really enforce its agenda very well. If the United States, for instance, decides it doesn't want to do something that the UN has mandated, it just doesn't do it, and that's it. It just yes. Oh, cool.
And I can tell you one of the reasons that worked is because they scared the ever-living shit out of me. But also there was an infrastructure that was already set up. So I think it was the banning of the fluorocarbons that they were really pushing. They had something in place to replace it.
That's brilliant.
Impact the economy as badly as what would happen now.
Right.
So there needs to be an infrastructure that needs to be set in place for what needs to happen now to occur. So, and I don't really remember politicians, other than banning fluorocarbons, I don't remember politicians really getting involved in it. I'm sure that they were, but to me, what I remember is it just being more of a moral thing. So that's what really,
Yeah, I love what you said about providing an alternative. I feel like so much, I love talking to scientists and people who are at the edge of what's happening right now, but so much of what goes down is criticism without replacement. And this is very dangerous because it's very easy to pick on any number of scientific theories. I mean, like we've discussed over and over in this class, they're almost all wrong probably to some extent. That doesn't mean that they're worth abandoning. That just means that they need to be either replaced or updated somehow. And that takes a particular kind of person who's willing to go that next step. That you wouldn't believe how many people I talk to who can talk for hours about what's wrong with something and have no clue about what should come next.
so we were also, at that time period, there were two things that were threatening us globally, and that was the ozone and nuclear war, the Cold War. And so they were already in this mindset of threat. So it just compounded.
Yeah, and it was nice, and in a way, having that mutual enemy, right, like with Russia being like this big nuclear threat, it was somehow unifying for the rest of the world at the time, which is interesting because Russia's back in the news again. And it's not clear. One thing. Gosh, I could just go off on this, but
Sorry.
yeah, maybe we shouldn't. I have thoughts about that, but let's. We're not going to make it. I want to make it to extinction. That's the goal at the end of this class. So let's see if we can do that in 50 minutes. We got to talk about the whole birth of life on this planet and everything. So, and I want to show you a couple of cool things first. All right, let's keep rolling. So, the atmosphere is mostly nitrogen. There's there is a bit of oxygen at this point. I guess 20.95% of our atmosphere, and some different traces of various other gases. Why? Well, okay. This is important when we talk about because it's not thought that oxygen was always a large part of our atmosphere, and so there's different theories about how that came to be, and we'll get into that. This is actually really important too, again, to consider how much of a Goldilocks zone this planet is in, because like I said, we have this wonderful stable temperature range, essentially, which allows us to have liquid water. Nobody else that we know of around us is able to pull this off, as none of the other planets or moons. And this is really important because if it was a little bit hotter, really not that much hotter. If it was a little bit hotter, you would boil off the oceans, and that just means you would still have all the weight of the oceans, but it would be above you and around you. And this would really be a problem in terms of even getting light down into the, I mean, just think at the bottom of the ocean, it's completely dark, right? We would have quite a crisis. It would liberate all of the different carbon dioxide that's bound up in molecules would be cooked also. I mean, it would be a very gaseous planet otherwise without that perfect temperature zone. Which is something to consider too about the deep past. If the Earth didn't actually form right here, maybe it formed somewhere slightly, just a little bit further one way or the other, it might have had a very different look in the beginning. And we'll talk about that, about the early Earth's atmosphere in a second. So there's basically 3 different theories that compete as to where our atmosphere came from. The first is that it came from the same event that formed the Earth itself. Perhaps it was greater or lesser, but it was essentially formed in place. The second one is that it came from some internal means like volcanism, release from different rocks, things like this. And then the third idea is that impacts from comets or asteroids brought the atmosphere. And actually, this was the more popular theory when I was a kid, especially with regard to where the water came from. I think enthusiasm for that is dwindling. There's recently, we talked about it before, but there's recently been a great deal of water discovered bound up in the minerals within the Earth, something like somewhere between 1 and 6 times the ocean's worth of water under our feet. Just not in a liquid form necessarily, but hydrated around these different metals. So this is open debate as to where this atmosphere came from exactly. We do know that at some point the oxygen shot through the roof, well, jumped up to 20%. It doesn't seem like the early atmosphere, based on the chemistry, had much oxygen at all. And a lot of people have attributed this to life, which is a reasonable hypothesis. We'll talk about that. What do I want to say about weather? Weather is a complex issue. We could do a whole class on weather because there's so many open-ended issues. Generally speaking, most of human history has treated weather as a product of temperature and pressure, which is totally reasonable. I'm certain those play in greatly to the cloud cover and the precipitation and the wind currents and so on and so forth. But there's also this really interesting phenomena involving electricity. You might have noticed at some point that in a storm you get lightning and thunder, which is quite fascinating. And so those electrical processes are beginning to be incorporated into our weather patterns, especially as they relate to the upper atmosphere. So this is I want to see if I can pull this up. There's this, does anybody know about this website, Null School? Oh man, you guys are gonna love this. Any of you who want to, if you ever want to know anything about, let me see how I can do this for you. Give me just a second. This is an incredible website. So you just go to your browser and type in earth.nullschool.net, and you get this really amazing interactive globe. And this, if you ever want to know what's going on in your neck of the woods, this is the best way to do it. So you can look at different pieces of the atmosphere. In particular, I like to start with wind, and we can look at it at different elevations. So the elevations are listed by pressure, which is quite interesting. This is actually how most pilots would think about elevation in terms of the surface pressure. This is how their instruments would work. Also, all of the different weather balloons and really a lot of meteorology thinks of height in terms of pressure. So it lists the height in terms of pascals. And so at the surface, you see a very different stream. Let me zoom in just a little bit so you can see. Let's see this a little bit. Let's wait for it to pick up. All right, so we can see the different currents that are going on at the surface. If we go up, though, we notice that some of these currents start to change. All right, we're about halfway through the atmosphere now. And what's really interesting is that at a great height, they even out. And so when you look at the Earth from a great height, this is way up in the stratosphere, it's actually a very smooth convection. And you have to start thinking about these wind cells, these temperature cells, as in 3 dimensions, right? Forming vortices in 3 dimensions and backfeeding onto one another. And we can look at, in addition to wind, we can look at the temperature. Of course, it's extremely cold way up there. You know, you can see the temperature scale down there at the bottom. But if we go back down a little bit, still quite cold. Warming up a bit. And then down at the surface, we see the heat that we're used to lately. Now, one thing that's really interesting, actually, that you can do with this map, if you want to play around with it, is you can look at particulate matter, which is quite fascinating. So what's really interesting is that you look at our hemisphere, and it seems like there's actually quite a bit of particulate matter being stirred up in the oceans, which is fascinating. And also, you know, let me see, get my cursor back. So you go over and look. The Amazon is particularly has a good deal of particulate matter. There's a number of forest fires over there. If you go and look up north into the border of Canada, there's also quite a few forest fires occurring. But check this out. Let me go around the world real quick. Ooh. Asia is not doing so hot on the particulate matter over there. And this is quite fascinating. And this is where a great deal of the world's population resides, in the subcontinent of India and in mainland China. And there's this is almost without doubt anthropogenic. This is coming from people. This is coming from industrial processes. And it's really, really wild to watch this evolve on a day-to-day basis. I mean, I've been watching this map for several years now, and it's not getting better over there. So what's really strange, going back to our conversation about global decision-making, is that obviously pollution's a weird thing, because especially air pollution, because it doesn't just affect us, right? If I kick out a bunch of pollutants in my backyard, it actually comes and travels across the ocean and kind of hangs out there. And I think that's probably why we see this mess over here in the Pacific Ocean. Well, it's not as bad as mainland Asia, but it's quite dirty still. And we're getting a lot of that as it reaches our coast. So something to think about in terms of how we want to imagine running this place as a globe in the future, which is a very dangerous concept, but it's also really important to some extent, because there's no way to just isolate your air from anybody else. All right, let's get back over here. So earth.nullschool, check it out. It's a really cool website. You can get lost there for hours. All right, so now I'm going to take just a minute to talk about the ionosphere, which is one of the frontiers of our exploration in terms of understanding our own climate, in terms of understanding how the sun interacts with us, how the sun helps our weather systems or hurts our weather systems. You know, I recently had the chance to sit down with the director of the heliophysics division at NASA, a woman named Laika Guhartakurta, who was kind of telling me about where they're at in the process of studying the sun's interaction with Earth's weather, and particularly with Earth's seismicity, right? Which is really, really a fascinating idea because as you mentioned, we've often thought about earthquakes as coming down to the grinding of these plates together, which they undoubtedly do. But the question is, can we predict when that's going to happen and why does it happen? And why are these plates moving when they do move? Is it a completely random process? Does the interaction between the Earth and the sun have anything to do with it? And so they're just starting to open a number of investigations about this, which is quite fascinating. You know, one thing that's really interesting about having this ionized layer of atmosphere at the top is that you develop something akin to a battery with the Earth, where the ground is very negatively charged and the upper atmosphere is positively charged due to this ionization. And so you have something like a potential difference of voltage between the top and the bottom, which is not insignificant. And if you've ever seen, let me think of a good example of this. Has anyone ever heard of the concept of piezoelectrics before? Yeah? Can you explain it to us? Yeah, or vice versa. If you apply a pressure, you get a tiny voltage. So it's something like in the lattice of some materials, they have charged portions of the crystal, and as you squeeze them, these charged portions of the crystal interact, and you can generate a net current out of it. And this is exactly how watches work for the most part. You're periodically exciting them, and they compress, or they have some potential applied to them, and you get this cyclic decompression. And so there's thoughts that perhaps there's some process like this occurring, right, where you have piezoelectric interactions within the mantle with respect to the sun. I mean, the whole thing it can be treated as a giant capacitor, which is quite fascinating. Okay, so why are the atoms out there in space? Why do they behave this way? You know, generally speaking, these atoms, hydrogen and helium, are rather inert. They don't electrically interact with one another. And, you know, you're generally going to hear in the textbook that this is because in ions, the electrons are stripped from the protons, and you have a delocalized sea of electrons, which is fine, and it is so. But I think that a more useful way of visualizing this is that under pressure, the atoms are actually bouncing against one another, and their surfaces are somewhat compact. There's a lot of space in between them because they're crashing into one another, and they're curling up in a way. Actually, when you take the pressure away, and there's a direct relationship, I'm not sure if I made a slide for this, maybe. There's a direct relationship between removing the pressure from these atoms and their electrical conductivity. So I think a better way of thinking about it is that they're sort of allowed to expand and stretch when there's no pressure being applied to atoms. This allows them to be in contact and conduct electricity. And so that's what's happening up there in the upper ionosphere, which is well beyond the stratosphere. And the cool thing about that, okay, yeah, I did. So this is a relationship between pressure, which you can see, and conductivity. Degree of ionization is what it's a readout of. This is what's called a cold plasma, by the way. On the sun, of course, it's thought that the plasma is very hot. So in other words, the delocalization, the merging of these different atoms together in this ionization, this plasma, has to do with really how many collisions are happening. And they're thought to be under great pressure in that case. But the opposite thing can happen, which is a cold plasma. And this is really interesting to people who are working on fusion, which is thought to be this mythical energy source. We might be able to essentially make a baby star in a reactor on Earth. And so the ideas about how to control a cold plasma are very interesting to people working on fusion. you know, uh, this is a really interesting phenomenon too, just to demonstrate this concept to you. If you look at the way that plasmas form in air, you see something that looks like a lightning bolt, right? You've ever watched a storm. We don't get a lot of storms down here, but there was a good lightning storm this summer, actually. Well, good. Maybe not good. It led to some fires. In the air, the atoms are conducting amongst one another, and they're exploring lots of different paths between the anode and the cathode. And that's what you see over here on the right. In a vacuum, there's not so many molecules available, and so the path which is explored is generally the path of least resistance. This one curls, but that has a bit to do with the way that charges rotate as they move through space, the way that atoms actually conduct in this rotatory fashion. So you have very different phenomena in terms of the appearance of conduction throughout the atmosphere, which is what we see, versus up at the top, which is something like a very smooth surface. There's a very smooth layer. And this is really interesting because what you can do is you can treat that actual smooth surface as if it is a true surface, as if it's a metal or something. And we use this all the time, actually, in order to shoot radio waves. You know, if you allow me to say shoot radio waves, but really in order to conduct radio waves, we can actually skip them across this layer. And this was vital to radio communications, especially prior to the advent of satellite technology, where we're using more focused beams of light, of radio and other wavelengths to communicate. So this is, and there's some really interesting intricacies to that. This was very important to you if you were trying to communicate via radios, particularly in the mid-20th century. Okay. And yeah, I essentially already talked about the capacitance of the Earth. Again, the Earth seems to have this positive layer. There seems to be a negative layer. There's some sort of battery-like behavior there. We call it a capacitor. And it's unclear how much this is playing into the generation of our own weather patterns. You know, there's a case to be made for the fact that the clouds tend to be positively charged. The Earth tends to be negatively charged. And so there must be some effect with respect to the separation of those layers, right? You know, the different layers of the clouds are alternatively more or less positively charged. And so when we look up at the clouds, we see really interesting effects in terms of the layering, in terms of the shape of the clouds, and certainly the capacitance of the Earth will play into that discussion in the future more than it does already. All right, I want to spend probably the rest of this class talking about life. And this is really the only class that we have to talk about life. It's not a biology course. I really wanted to bring my wife in to talk to you about the origins of life. This is one of her favorite topics, but there wasn't enough time to pull that off. And maybe in the future. So were there anybody have questions about the atmosphere before we move on to life? So let's talk about the story that is most popular right now, first of all. And then let's investigate what else could be going on. And the details of even the most popular story are difficult to wrestle with too, because the history of studying life comes down to the combat between two ideas. One, that life can just arise spontaneously out of nothing, and one which essentially says, no, life comes from other life. And this seems like a foregone conclusion to all of you, that life doesn't arise spontaneously, but what's really fascinating is that our origins of life stories require it to. And so there's something of a tension between those two concepts, because on one hand, we are very well aware that you're not getting life that's just going to happen on this table without some other piece of life seeding it. But at the same time, we need to explain how life came to be in the first place on our planet. And if it didn't form on our planet, well, where did it form? And it must have formed somehow. And so it's strange that in some sense we've moved completely away from this concept of spontaneous generation, but we're also married to it. We can't get away from it also too. So the idea is that for tens of millions of years after the Earth's formation, life, the seeds of life began to take shape. They were essentially very simple. They existed in these warm, nutrient-rich seas. Perhaps very simple molecules came together and by chance found themselves interacting. And we'll talk about the details of how those processes are thought to have unfolded. And then at some point, the cells, the very prototypical cells, which were something very close to bacteria, they evolved the ability to use the sun's light to do something called photosynthesis, where they're actually able to construct complex molecules using the power of the sun to take apart water and give off oxygen as a product, which is quite fascinating. Because once you have oxygen at that point, then everything just goes crazy. Oxygen's an unbelievably reactive molecule. You know, you've seen rust before, right? This is essentially how your body works, is through respiration by essentially modifying molecules and drawing current from the from these processes that involve the reactions with oxygen. So, you know, at some point there was enough power available that the animals began slithering out of the sea and were able to pick up nutrients on land. They started eating one another, and you know, you end up with human beings eventually. And this is the general story that we tell. The difficulty with telling any story about the origins of life is that you don't have a lot to go on in the beginning, right? So we talked last time about how the surface of the Earth is constantly being remodeled, right? Those plates, as they've shifted, they eat up the surface of the Earth. There's something like 2 rocks left that are even approaching 4 billion years old. Most of the rocks that we can find are far younger. And the earliest instances that we can see of anything living date back maybe 3.5 billion years. And what does that mean? Well, if you're looking for something that's alive, you have to look for fossil records of that. Now, obviously, the first life forms that existed didn't have big skeletons that are going to make nice fossils, right? And so there's scant few fossils from the early days. We have to look for little traces as they moved their way across some mud. And actually, in order to even form a fossil, it is something of a real magic trick that requires the animal to essentially, you know, leave some trace or leave its skeleton or something behind in the perfect conditions that are able to be infiltrated with the perfect concoction of minerals that are able to turn that body into like something that's essentially calcified. It's essentially mineralized, and you have a record of it that way. And it has to be preserved very nicely. It can't be squished. It can't be coated with magma. It can't be destroyed in any way. So there's, you know, when we talk about the fossil record, sometimes we're missing huge chunks of the record. There's a layer, you know, in the Grand Canyon. The Grand Canyon's amazing. I don't know if you guys have had a chance to go there. Do it. It's really cool. But there's some parts of the record in the Grand Canyon, because you can see all the different layers, you know, and you can date these rocks, and at some places you can find fossils. There's a place in the Grand Canyon that's missing 1 billion years of rock record. You know, that's no small amount of time, and it's hard to say how many other billion-year pieces are missing before our earliest date. So again, just like with everything else, the dating and the sequence of events is what we do when we take the evidence that we have and we try to map a story onto it. We almost never find in science people introducing ideas for which there isn't hard evidence to support them. Doesn't mean there wasn't anything happening before 3.5 billion years ago. It means we don't have any record of it. And that's a really important distinction when you formulate your concept of how certain we are about these stories. They're very good stories, but they can only work off of what we can see. What you see up here actually is one of the first fossils that we have. These are called stromatolites. This is thought to be from the Precambrian era, maybe around 3 billion years ago. And these are, they're essentially a sort of blue-green bacteria that was able to photosynthesize. So this is actually quite a bit downstream of the first life forms, because it's unlikely that the very first organisms were able to photosynthesize. Now, how do we know that? Well, we can actually find bacteria right now that don't photosynthesize. In fact, there's bacteria living something like, at least as far as we can, basically as far as we dig down into the earth, we find things alive down there, which is really fascinating. Not only do we find things that are alive down there, they're also very primitive. And the genetic trees start to get really crazy and confusing when we go down deep beneath the earth. And so there's a number of biologists and geobiologists who are trying to come up with stories about how maybe the life came from within, deep down, actually, while the atmosphere or the ocean was very toxic and reducing, and it wasn't a great place to live, but they found a good environment down below. And some of these bacteria they're finding down in what they call the deep hot biosphere, some of them can breathe rocks, which is really wild. That's how they get their power. And so certainly there was different forms of life that we're not able to see that predated this. I do think that it's probably a good point to stop and ask, what is life actually? Which is a terrible question to ask a biologist if you have them on the spot. Because biology is obviously the study of life. But what is life exactly? Does anybody know? Yeah, I love asking biologists this too, but then I always have to apologize and say, it's okay, I don't expect you to have the answers to it. It's not so simple. So most textbooks, most biology textbooks will list some things. They'll have a big listicle of what qualifies as life. And this is okay. I think this is what we call an operational definition. It works. It works for us, but it's not totally clear because it's not unambiguous. There's some circularity in it, and it's difficult because then you have nested concepts. So, you know, this is just reading off of Wikipedia. They say life is a quality that distinguishes matter that has biological processes, such as signaling self-sustaining processes from that which does not, and is defined by the capacity for growth, reaction to stimuli, metabolism, energy transformation, and reproduction. And the problem with each one of these things is that each one of those qualia can be ascribed to something that's non-living too, right? You know, hurricanes actually do grow. They actually do travel in response to stimuli, whether that's pressure gradients or whatever it is. But they don't seem to reproduce. Okay, so they're not alive. So they don't match the criteria. There's some other really interesting ideas about life too. You know, one thing that's really fallen out recently, I think the discussion is centered around, it has to do with the agency of living beings, right? We all possess some sort of autonomy. We have some sort of goal-directed behavior. And this hasn't totally made its way into the hearts of biology. It was actually proposed by Democritus, who was the Greek philosopher who gave us the idea of the atom in the first place. He said life had something like a soul, which was, actually he used the word psyche, which meant soul in that day. It had some intention. And there's actually some really cool research going on right now in terms of considering the motivations on a cellular level. You know, one of my favorite biologists, I think this guy's going to win a Nobel Prize for sure. His name's Michael Levin. He's at Tufts University. And he's trying to not only understand life, but he's also trying to work on the concept of regenerative medicine. Because right now, if you, let's say you're working with a bandsaw and you lob your finger off, well, they'll try to like attach the finger, right? But it makes a lot more sense to just tell the finger to regrow, right? And you see this in all of the like sci-fi movies. And Michael's working on that. And the way that he's going about it is he's actually asking questions like, what does the cell want? What does it want? What is its local environment telling it that it needs to do? And if we can give the cell what it wants, if we treat the cells like they're autonomous, goal-oriented individuals that need something and they have values, they have desires, and if we can provide that on a local level, then perhaps we can actually get those fingers to regrow. Or take something like cancer. Why is this cell behaving? Why is it misbehaving? Well, it might not be getting what it needs. And so if you think about it from this point of view, perhaps you can engineer an environment that's appropriate to regrow those tissues or stop them from growing. And he's having some really cool success. You know, he did this really crazy experiment where he essentially takes these little worms and he cuts off he can direct the communication between these cells. He can cut it off at different regions of the cell. So he can stop the cells from electrically communicating with one another through these chemical synapses. And when he does this, he can cause the worms to grow heads on like different sides of their bodies. They're perfectly functional organisms. But he can essentially change the whole floor plan of the organism just by stopping the communication between different parts of it as it's developing, which is really strange because it seems to tell you that the pieces of the organism are growing not necessarily because they're programmed to grow a certain way, as we've always thought about it in terms of genetics, but because they're getting some input from those cells around them, which is absolutely vital to tell them when and when not to, because every cell of your body has the information necessary to grow a head, for instance, but every cell doesn't turn into a head. And that might have to do with the community around it. This is a very new way of looking at it. So these are all different ways of thinking about what life is. A really interesting one I heard recently was from this gentleman in Glasgow named Lee Cronin. And he says he's working with the people who are looking for life on other planets. And he says, if you want to find life, you just look for any molecule which is above a certain molecular weight. Any molecule which is sufficiently complex cannot be formed naturally without a life form. So if you want to find life, you look for something, you look for those traces of complex molecules. You know, it's not very big. I think it's something like molecules above 300 atomic units, which is really fascinating that you can't get these big molecules without a life form. So he actually defines life as that which makes these complex molecules. And I think that's rather interesting too. All right. So like I said, people argued about this. This was a really interesting experiment from 1668. There was a great debate which raged all the way into the 19th century about whether there was some vital force responsible for life, whether there was a vital force or whether life had to come from other life. And he designed this very simple experiment where he noticed that meat would grow these maggots on it, which is kind of gross, as it will do. But that if you sealed off the container, nothing would grow inside of it, which we all put to use in the kitchen. However, if you put a piece of gauze over the top of it, then these organisms would be trying desperately to get to the source for which that life would grow. This definitely moved the ball down the field towards the idea that life needed to originate from other life. But again, this is deeply contradictory because, again, we have to explain where life came from in the first place. And of course, in order to do that, we need some sort of spontaneous generation, which is really just kind of mind-blowing if you think about it. So this is the basic floor plan. Sorry, this isn't higher res. The basic floor plan for what the earliest proto-cells may have looked like. These bilayers that you see, which are the hallmark of all of your cells, essentially, these actually do form naturally. A soap bubble isn't so dissimilar from this bilayer situation, right? Where you have something that's hydrophobic on one side and excludes water, and part of it which loves water on the other side. And you know, the difficulty is that you need to start with some sort of nucleic acid, and nucleic acids, particularly the complex form like DNA, they don't form easily on their own. It's very difficult for one to just self-assemble. And so almost all of these stories start with a simple one like RNA, and then they imagine ways in which the RNA could find itself inside of one of these little bubbles, and maybe it associates with some peptide that allows it to grip onto the cell such that when it divides, when the bubble breaks open, it takes some of it with it. Maybe it takes some more proteins with it, and eventually you get the construction of some sort of complex molecules. This is something like the best that we have right now for explaining this. Because what's interesting is we find these individual nucleotides. They can be found all over the place, actually. They're found even on meteors, right? They're found on asteroids. These are very common molecules throughout the world, but the assembly of them into RNAs is a whole nother matter, which hasn't totally been worked out. And it's thought maybe some of the surfaces of the primitive environment were able to align them in such a way. There was like some crystalline surface in which these nucleotides could line up, sort of like a template. And maybe there's some truth to that. Still very much a puzzle and very troubling for these evolutionary biologists who are working on this problem. A good argument that's made for, okay, so here's the problem. If life did spontaneously generate on Earth, why don't we see it happening everywhere, all over the place today? There's been plenty of time since this happened. We should find new life forms all over the place. We should go out into the ocean and find something being made. We should see something like this happening. And this is really troubling because we don't. But it's possible that every time something like this happens, a fish comes along or another bacteria and eats it. I think this is probably the reason we don't see anything like this, assuming that life did originate on Earth, is that these kind of things really are happening all of the time. They're happening deep in the ocean. They're happening under our feet in the deep, hot biosphere. But every single time that a new proto-cell forms, it gets gobbled up by somebody. And I think that would make a lot of sense. So photosynthesis was a huge step that transformed the atmosphere from something very hellish into something that we see today, which is quite a bit less so. And it seems like the free oxygen didn't really build up until about 2 billion years. So if you think about those first photosynthesizing organisms, 3 billion years, it took 1 billion years for them to build up an atmosphere that was useful in the common sense, and for the evolution to catch up and build these. And like, I've already used the word evolution once. Does anybody understand the basic concept of Darwinian evolution by now? So it's quite simple. It's like if something happens, your shape changes as a little proto-cell, and it's productive and it works out for you, then okay, you survive and you replicate. And if it doesn't work out, then that's the end of the line for you. And this is the basic process of evolution that's thought to have shaped all of the organisms going forward. And there's an adaptive quality to it too, because the environment's constantly changing. Some organisms will have those mutations that allow them to survive in those situations. Others will not. And so that's what we're left with. Now, the regions, I touched on this a bit already, but there's a few places where we can imagine these conditions being interesting and in the Goldilocks zone for life to have formed. One of them is these vents, which were quite warm and had a lot of the reactive components that may have allowed, may have provided an energy source for those very early protocells. A bit later, we see the buildup of these stromatolites, and then, eventually the atmosphere takes off, and we can see things actually growing above the ocean. I don't want to add anything else about this. One way that we know that there was no oxygen in the early days, it has to do with analyzing iron, because iron binds with oxygen normally when there's no oxygen around. When there's no free oxygen in the atmosphere, you find it in rocks. It binds in a 2-to-3 ratio. But it binds in a 1-to-1 ratio with the rocks. But if there's a lot of oxygen, it binds in a 2-to-3 ratio. And so we can go back and look at these rocks and make some sort of history for when that oxygen appeared. And so, there's other things that compound. Once you get oxygen, you also have the ability for this ozone layer to form, which shields the organisms from this terrible ultraviolet radiation. I think this allows them to drift up and towards the top of the sea. It allows them to maybe start to move off of the sea and colonize the land. We talked a bit about the genetic diversity and looking at the tree of life. This is you see this all the time, this chart. And it is quite useful because it tells us how related we are to one another. And it turns out we're all very, very related to one another. But there is some difficulty in interpreting the relatedness of one genome to the other, because, of course, the simplest way to interpret it is, okay, well, we're related to one another because we had a common ancestor. And this is the basis of Darwinian evolution and tracing back the history of all of our species. Well, there's also a very real possibility that organisms are related because that's the only way to get the job done, right? And this is very troubling for scientists that are looking at exobiology and trying to detect life on other planets, because they have to ask themselves, does the life look anything like our life? Is that how life always works, right? Is all life going to have RNA? Is all life going to have ribosomes that are capable of assembling the proteins with the RNA? Or do they do it in a completely different way? And however you answer that question comes up with its own series of problems, because if you answer that, well, on the other side of the galaxy there's life forming and it looks just like life on this planet, well, that makes a real nightmare of these trees, because it means that these different organisms formed up in these fashions and have related genomes, not necessarily because they're ancestors of one another, but because that's how those organisms had to have formed. They use the same toolkit. Their cells form in that way. The codes of their cells form in that way because that's the only way to form a cell. And so this will be really, really interesting to rewrite the paradigm of this as we hopefully find something alive outside of our own planet. I'm sure we will eventually, whether it's through a biosignature or whether we actually go there and see it crawling around. So very useful. These genetic trees are quite useful for getting a grip on what's going on. But there's an interpretive level, just like with everything else. Also down in the deep hot biosphere, these organisms, there's 3 basic branches here. You have bacteria, then you have these other guys which are called archaea, which are essentially similar to bacteria, but they all cluster together in terms of relatedness. And then you have us, the eukaryotes, which are a bit more complex. This is where you see everything from plants to animals to fungi. You see real structures developing inside of the cells that you don't have. And the main one is the nucleus, which is able to pack a great deal of genetic information in a very complex fashion and read it and sort it. You have different cell structures. These are all very complex creatures over here that we call ourselves a part of. All right, I'm gonna have to skip this next part. I do want to say that it's worth. I was hoping to read a little piece of this, but I would have to skip it. Um, you know, there's a deep cultural history of there's deep cultural histories that consider the relatedness of organisms to one another in very different light. The Western tradition we come from has a very atomized perspective, where the organisms are very distinct and separate from one another. Many of the indigenous cultures look at it very differently, where the organisms are not distinct, but they're actually defined by their relatedness to one another. And I think there's a lot of value in that. You know, a lot of people think, well, I'm a human and that's a tree. And it's like, hey, you couldn't exist without that tree, which is something really worth thinking about. I mean, you need that tree to breathe, basically. And so it's not so clear that there's a distinction fundamentally from a physiological, physical perspective. It's not so clear how distinct those other organisms are from you. And we run the risk of thinking about them too separately and thinking about ourselves in this bubble, which I think will do us some disservice if we're not able to integrate that perspective. But let's keep going. This actually gave way to a really cool perspective. Have any of you heard of the Gaia hypothesis? Yeah? No? It's kind of cool. This is this idea which was put out actually by this guy named Hutton in the 1700s and sort of forgotten about since then, but repopularized by Lynn Margulis and Lovelock in the 60s and 70s. And it's kind of the idea that the Earth can be treated as a superorganism, that it is essentially, you know, all the little pieces are essentially organelles. They're little pieces of a bigger cell. And this has really cool implications because life is never found alone. If the Earth actually is a superorganism, that means that it's part of a community of other superorganisms. And we should expect to find interactions.
The Gaia hypothesis, which is this world is 1 in a million perfect.
What? I didn't hear that. Sorry. It's very rare and perfect. The Gaia hypothesis is more of an overarching view of the Earth as a living organism altogether, as one living organism. You know, the biggest argument against this, it's actually not a very popular theory, although it's quite interesting. And I should mention that Margulis, who came up with this theory, also came up with the idea that our powerhouses of our cells, the mitochondria, were actually absorbed little critters by themselves that existed alone, and then they were absorbed into the eukaryotic cells in a symbiotic fashion. So she was very concerned, very occupied with this idea of cooperation between organisms. I think this is what led to thinking about the whole Earth as a cooperative system, which, you know, the main problem with this that people always come back to is, like I said, life doesn't exist alone. You don't ever have one organism. It's just not how it works. Life exists in interactive communities. And so if the Earth is to be treated as an organism overall, where's the rest of them? How are they interacting? How are they reproducing? And actually, this brings us to another interesting point, which is that people entertain the concept that life didn't actually start on Earth. Maybe it started on Mars. Maybe it started somewhere else and came here. And this seems pretty crazy because life seems so delicate. But there's reason to believe that there's certain forms of life, particularly these things called bacterial spores, which are really, really tough. You know, they've unearthed these spores. It's sort of like a seed-like dormant phase of bacteria where when the nutrients dry up, that they can sort of form themselves into this protective case where they exclude all of the water or they lock up the water so it can't move. And they just sit there with their genetic information. And they can sit there for millions of years. There's some reports, you know, I think there's a few isolated reports of spores being dug out of amber, little bugs like bees that are found in amber that are millions and millions, tens of millions of years old. And they can take those bacteria, they put them in some nutrients, and poof, they come back to life after millions and millions of years. So there's some and they can survive going to space too. NASA took some of these spores, not the millions of years old ones, but they took some spores up into space. They put them in a little capsule on the front of the spaceship so they were exposed to all of the nasty radiation and everything. No problem, no issue for the spores. Brought them back, they grew just fine. So it does seem like life has the ability to sustain interplanetary travel. And this is a real dividing point for people who are working on origins of life stories. You know, they fall into one of two camps. They love this idea or they hate it. And so it makes sense, because even if you say, okay, life came from somewhere else, it doesn't totally relieve you of the explanation of, well, how did it form there in the first place? You know, has it just always been here since ever? I mean, some people advocate this, but again, we're left reconciling the spontaneous generation with the very evident truth that life seems to always come from other life, at least as we see it. All right, so you know what? Let's stop here. I want to do extinction, but I'll save it for the beginning of next class. I don't want to rush through it. It's too big of a topic. All right, thank you guys. Have a great weekend.